Section 8.3, Geometric Sequences and Series. We will define a geometric sequence with the help of a common ratio. We'll learn to construct the nth term. We will consider the partial sums and the possibility of infinite sums of geometric sequences. And we'll define a geometric series. So for a geometric sequence, we have a ratio between successive terms. And it's the same non-zero constant, and that would make a geometric sequence. So for a sequence a sub n, if a sub I plus 1 divided by a sub I is equal to r, for all positive integers I, then a sub n is geometric and the common ratio not equal to 0. So for example, we will have a sub n is equal to 3 times 2 raised to the n minus 1, which will generate the terms 3, 6, 12, 24, 48, and so forth. It has a common ratio of 6 divided by 3, which is 2. Or we could say the common ratio is 12 divided by 6, which is 2. 24 divided by 12, which is 2. 48 divided by 24, which is 2. It is a common ratio. And that's what makes it geometric. So because of that regular common ratio, we can generate the nth term of a geometric sequence as a formula. So the nth term with a common ratio r for geometric, a sub n is equal to a sub 1 times r raised to the n minus 1. And that r has to be non-zero. All right, so let's find the nth term of the geometric sequence whose first 3 terms are 36, 30, 25. So we do know our first term is 36. The common ratio is found by finding that ratio. 30 divided by 36 is 5 divided by 6. So using our new formula, we can write a sub n for this sequence is 36 times 5 divided by 6 raised to the n minus 1. Let's try this again. We're going to find again the nth term of a geometric sequence whose first 3 terms are 200, negative 20, 2. So again, we know the first term is 200. We can construct the common ratio. Negative 20 divided by 200 reduces to negative 1/10. So using our new formula, we now have a sub n is equal to 200 times negative 1/10 to the n minus 1. So what we're seeing is if we have those pieces of information, the first term and the common ratio, we can come up with the nth term of geometric. Finite geometric series and the partial sum. So recall the partial sum of a sequence, again, the sum of finite number of consecutive terms beginning with the first term, and we designate this S sub n. So summing of these terms of a sequence is called a series. So with a sequence 3, 6, 12, 24, 48, geometric with r is equal to 2. If we wanted S sub 5, we know that n is equal to 5. We want to sum the first 5 terms. We would have 3 plus 6 plus 12 plus 24 plus 48, and that will sum to 93. That's a series. For geometric series with a common ratio r, we can also get a formula for this. So what we're going to do is we're going to write our partial sum written out expanded. So it's the first term plus the second term and so forth. So the first term, a sub 1. The second term, what we're doing is, again, we're multiplying by r. And then the next term we multiply by r again, and we can keep doing this. So by the time we get to the end, we have a sub 1 times r, and then a sub 1 times r squared, all the way down to a sub 1 times r to the n minus 2, and then plus a sub 1 times r to the n minus 1. So each time we're just multiplying by r one more time. So I'm taking this exact same expansion, and underneath it I'm writing negative r times that expansion. So I'm putting one more factor of r. It'll change all my exponents, and in fact, my first term now is negative a sub 1 times r, and then negative a sub 1 times r squared, and so forth. One more factor of r. So when I get to the end, I have now negative a sub 1 times r to the n, because I've added one more factor of r. And what I want to do is I want to subtract these. So, or add these, I could say, a sub n minus r a sub n is equal to, and again, we have this pattern showing that all of these middle terms, there are exact opposites. All of them will go away. And the only thing we're getting is the first term and the last term. So we've got a sub 1 minus a sub 1 times r to the n. So what we're going to do is we're going to factor each side. We can factor s sub n from the left. We can factor a sub 1 from the right. We're solving for s sub n. We divide by our binomial, and we now have a formula that we can use to find the partial sum of any geometric sequence. So s sub n is equal to a sub 1 times the quantity 1 minus r sub n, or r to the n, all divided by 1 minus r. So let's go back to our sequence that we just had. We had 3, 6, 12, 24, 48, and so forth. We said it's geometric. We know the first term, a sub 1 is 3, and we know the common ratio is 2. So beforehand, we just summed all 5 terms. We got 93. Now we're going to use the formula. We incorporate the first term, 3, and then times 1 minus the common ratio 2 to the 5th power, because n is 5, divided by 1 minus the common ratio 2. So we now have 3 times the quantity 1 minus 32 divided by negative 1. That's 3 times negative 31, which is negative 93, and then we divide by negative 1, and we get the 93. So let's evaluate the finite geometric series using summation notation. I want the sum, k equals 0 to 6, of 5 times the quantity 2/3 to the k power. Now, this one is kind of special because if you notice, the index does not start at 1. It starts at 0. Which means if I'm summing from 0 to 6, I have 7 terms that I'm summing. So I need to use the first term. We figure this out. If I let k equal 0, 2/3 to 0 power is 1. 1 times 5 is 5. The first term is 5. The common ratio is that 2/3 that's raised to a power each time it gets multiplied. And looking at from 0 to 6, that means n is 7. We have 7 terms. So make sure you check the index. So we've got s sub n is equal to a sub 1 times the quantity 1 minus r to the n, all divided by 1 minus r. So 5 times the quantity 1 minus 2/3 to the 7th power divided by 1 minus 2/3. We're dividing by 1/3. Dividing by a fraction is multiplying by a reciprocal. So we will have 3 times the 5 times the 1 minus, and when we raise 2/3 to the 7th power, we have 128 divided by 2,187. So we're going to make common denominator here, and when we add, we now have 15 times 2,059 divided by 2,187. So when I multiply that out, I've got the exact value in reduced form of 10,295 divided by 729. And then this one I did do an approximation for. It seemed appropriate to see about what that number is. So approximately 14.122085 and so forth. Right, what we want to look at now is the possibility of what's called an infinite geometric series, meaning we're going to sum an infinite sequence and we're going to get a result. So for geometric series with a common ratio, absolute value of r is less than 1, we can see that r raised to the n power will approach 0 as n approaches infinity. And what that means is, as you take a proper fraction, so the value of r, the numerator is a number smaller than the denominator, and you raise it to a power, if you increase that power over and over and over again, that fraction gets smaller and smaller and it approaches 0. So since we're going to infinity, we're saying it's 0. And that's because the denominator will grow so much faster than the numerator as the exponent gets larger and larger. Take a look at what we had here. We had 2/3 to the 7th power. We raised 2 to the 7th power, we have 128. We raised 3 to the 7th power, we're at 2,187. If we let that grow to infinity, this would go to 0. So if we look at that, our formula that we started with, S sub n, the partial sum, was the first term, a sub 1 times 1 minus r to the nth power, and then divided by 1 minus r. So if we're saying that this r to the n is going to approach 0 as n goes to infinity, then all we're left with is a sub 1 divided by 1 minus r. And that's only good if the absolute value of that ratio is less than 1. It doesn't matter if it's a positive number or a negative number, but it has to be between -1 and +1. So let's see if we can sum an infinite series. Problem 1, we have the sum k equals 0 to infinity of 5 times the quantity 2/3 to the k power. Now that's the problem that we just did, and all we did is we summed the first 7 of those terms, and we got something slightly larger than 14. Now we're going to sum an infinite amount. We still have a sub 1 is 5. We still have our common ratio is 2/3. It's less than 1. We can use this. So our infinite sum is 5 divided by 1 minus 2/3, which is 1/3. We invert and multiply, and the sum of the infinite series is 15. Number 2, this one, notice the index are different. It doesn't matter where it starts. It's that it's going to infinity and that you have a ratio that's acceptable. So this one, the sum k equals 1 to infinity of 3/8 to the k power. So here, our first term is 3/8. Our common ratio is 3/8, and again, it fits the pattern. So we have 3/8 divided by 1 minus 3/8. So we have, what do we have here? We have 3/8 divided by 5/8. And the way we write this is 3/8 times 8 divided by 5. And it looks like we get 3/5. So if you sum that infinite series, you'll get 3/5 exactly. So this next couple of exercises I want to go through is to really confirm that what we're doing with these infinite series makes sense. So this is kind of working backwards. So we're going to write a repeating decimal as a ratio of 2 integers. So the first one I want to look at is the repeating decimal 0.3, where the 3 repeats forever. Now we know this 0.3333 forever. Everyone should know that that should equal the fraction 1/3. a ratio of two integers. So we're going to write this as a repeating, or let's say an infinite sum. So we start with 3/10, we add 3 100ths plus 3 1,000ths plus on and on and on, and it never ends. But what we know is that this is a sequence with the first term is 3/10, and it has a common ratio of 1/10. So if I have my first term is 3/10, my second term is 3/100, I multiplied by 1/10 to get there, and multiplied by 1/10 again to get to the next term. So that's our common ratio. It fits the pattern. So we can write an infinite sum as the first term divided by 1 minus the common ratio. So we have 3/10 divided by 1 minus 1/10. That's 3/10 divided by 9/10. That's 3/10 times 10 over 9, which reduces to 3/9, which is 1/3, which is what we expected. Now we're going to try it again on a number that is not so familiar. So we want to write the decimal 0.345 with a line over the 4-5, meaning the 4-5 is repeated, and it starts over here in the 100 and the 1,000th place value. So we want to write it as a ratio of two integers in simplest form, so we break it out. We have the first fraction, 3/10, that doesn't repeat. What's repeating is the 4-5. So we have 3/10 plus 45 over 1,000, because it's 3 places over, plus 45 over 100,000. We have to move 2 more decimal places over. So we have a total of 5 zeros now. And then 45 over 10 million, because again, 2 more zeros. We're skipping 2 place values each time. And all we need to do is find the integer equivalent of our infinite sum and then add it to the first fraction here. So within the brackets, a sub 1 is 45 over 1,000, and we know our common ratio is 1 over 100. So again, if I multiply 45 over 1,000 by 1 over 100, I'll get 45 over 100,000. Multiply by 1 over 100 again, and I get the next term. So that is my common ratio. So we have 45 over 1,000 divided by 1 minus 1 over 100, or 45 over 1,000 divided by 99 over 100. So we multiply by reciprocal, and we can reduce this by a factor of 100 here. We have 45 over 990. This reduces to 1 over 22. So we go back and we say, for our decimal 0.345 with the repeating be the 4-5, we take the 3/10 and we add the 1 over 22. And this will sum to 19 over 55. So if you take the decimal, or let's say if we take 19 and divide by 55, there we go. And there's our repeating decimal, 0.3454545, and it goes on forever. So for geometric sequences and series, the formulas that you have to know, obviously you have to know how to get the common ratio. You need to know how to get the nth term. You need to know how to get the partial sum. And now you need to know how to get the infinite sum and when you can get the infinite sum. If it doesn't fit the criteria for that common ratio, then you can't use it.